Last thing we did was looking at Faraday's law of induction, and we summarised Faraday's law saying that the EMF is equal to minus N divided to T. And we know phi is the rate of flux, not the actual field strength. That's the density of the field. This is the number of field lines through the coil. And the faster we change that number of field lines through the coil, the more voltage we produce. We only get, even though the coil may be opened, we'll still have EMF, but if the coil is closed and creates a circuit, we get current flowing. And the number of times we have the coil, in other words, you have one or two loops, the more EMF is itself generated. So now we know how to generate electricity. We have to change somehow the flux, and we come up with a few ways of doing it. The first way was, we could turn the electromagnet up and down if we could make this field strength bigger and stronger. But then we found out the easiest way was to take a coil and to spin it in a field. Okay? So as a coil, or as a hoop, just making it a hoop, if that turned into the board was a field. So at the moment there are, let's say it's 11 field lines going through there. When this loop spins on its axis and it goes into this position, then there is no more lines going through that hoop or that coil.
When you mean that position, you mean as in like the circle?
Yeah, so here is that's that position, and the field lines are coming straight into my face. As I turn to a pirouette sideways, now the field lines are going straight beside the coil, they're not entering the coil itself. And as I turn again and face the board, they're now going this way, and so on. So as I go around, I have 11 field lines, no field lines, 11 field lines, no field lines, 11 field lines. And the faster I do that, the quicker it goes 11, 0, 11, 0, 11, 0, and so on. Okay? So, after spinning around, I'll be out of breath. Now we're doing generators are ways that we can generate EMF, the devices that we do it. So we take that idea of taking a coil and just spinning it in a magnetic field, and that's a generator. Before we start, we're going to go down and have a look at parts of the generator itself in a few moments. We must make sure that we have these two concepts clear in our head. These we already have from the motor. We already know from motors that the word stator means stationary. So part of a generator that does not move is stationary, it is part of the stator. Part of the generator that does move is called part of the rotor. Rotor meaning to rotate, of course. Okay? Now, in different designs, there are different stators and different rotors. Okay? In the most common design for a generator, we take the coil and spin it and keep the magnets the same, make them stationary. But in other designs, we can keep the coil stationary, we can spin the magnets. So the stator and the rotor can change position, or can change function. Okay, so those two words are going to be used just like we did in the motors. Okay? This is the diagram that you have in your book, and what do you know? This is a generator. What do you notice first about a generator? What do you notice about that diagram? You've labelled it before. Right, this looks like, and in fact is, a DC motor, isn't it? There's only one difference. In the DC motor, this thing here was different. Okay? In a DC motor, that was a power source. So the function of a generator is the same as a, sorry, not function. that the structure of a generator basically is the same structure as a motor. Okay? So let's have a look at some of the features of this, and then we'll go and see why they are so similar. Okay, so firstly, do we recognise the coil? Okay, the coil's this thing here, partially hidden by that magnet. Once again, this is the magnet, this is the permanent magnet. Is there a way of producing magnetism that doesn't require permanent magnetism? Yeah, that could be electromagnets as well. Good. We recognise this little doober over here. Okay. What is it? Split ring commutator. Good, excellent. And don't forget to put the whole sentence together and don't be lazy. Now, there's two arrows here. The whole thing is a split ring commutator, but this part here is just pointing to part of that commutator called the split ring. So that's the split ring there. And this one here is pointing to the connection. It's the brush. Yeah. Okay. Together, the brush and split ring become the split ring commutator. Okay. This is pointing to that arrow. This is the rotation. Okay. And lastly, we're pointing to that pin which goes all the way through here, and it would be the yes, it's the thing that rotates around. It's the axis. Okay. Now the armature. What is an armature? Right, it's a supportive structure. The coil would be wrapped around an armature. So we haven't shown the armature, so we can simplify the whole thing. So we aren't seeing the supporting structure in the commutator that keeps us, because those split rings just don't hover in midair magically like they are at Hogwarts at the moment. Okay? So the armature are supporting structures of which these things are attached. So as it does here, it doesn't fly apart. Okay? Right, so if you can label a DC motor, can you label a DC generator? Yes, they're identical. The only difference is this. Okay? That used to be a power source. What happens is, what the things do. A motor, the purpose of a motor is not being a dolphin. The purpose of a motor is to produce what? What does a motor produce? What's its ultimate gain? It's produce motion. Yeah. A motor, we want something to move in the end. Okay? So its purpose is to produce motion. How do we produce motion? We put electrical energy in, and out comes motion. And what is the cause of that motion? The motion is caused by the motor effect. Oops, that's not wrong. Okay. So, a motor. Electrical energy goes in. That electricity means that is taken in by a current carrying conductor. They are in the presence of a magnetic field. Therefore, the motor effect will cause the coil to move. The resulting thing is motion. Okay. Now, what's the difference? Well, what's a generator? What's the purpose of it to generate? Right, its point is to generate electricity. Okay? So how do we generate electricity? We need motion. Good. So we want motion to go in. We need to somehow turn that coil. As we turn the coil, a change of flux happens, and that change of flux generates EMF. How does that happen? Well, the motion up here is created by the motor effect. The generation of electricity is done by Faraday's law. And Faraday's law says a conductor in the presence of a changing magnetic field has induced within it EMF. And all we need to do is have some motion, and this motion changes the flux somehow. Have a look at the two. One is the reverse of the other. Electrical energy in for a motor and motion out. For a generator, motion goes in, electricity comes out. They are reverses in function. And in most cases, especially in the DC motor, it's a reverse of form. The forms, the actual structures of the two things are the same. Are we okay with that? Okay. Now, while we are here, we've got to somehow spin our coil. That's pretty bad. Our coil. We've got to make it turn. So how do we do that in the modern world? What does Australia mostly do to turn its coils out at Lithgow Power Station? Right, we burn coal to create heat. Heat is then used to boil water. Water boils, creates steam. Steam is a gas which is highly expansive. It turns a turbine which turns the coil. Okay? And that is called coal-powered fire stations. Australia is mostly has them. Other than that, we can just attach a big old propeller to this and pop it in water, and we use a river. As it flows down, the river turns the propeller, and the propeller attached to the coil turns the coil. We call that hydroelectric, as in snowing. Okay? So we either have to boil water or move water at the moment. Okay? What is another method that Australia doesn't employ? Right, nuclear. We just use very controlled nuclear reactions which create a lot of heat, boils water, water creates steam, steam creates a propeller or a turbine to move, and so on. What does a lot of Europe use? Wind power. Good. Wind is just simply using a big propeller to turn a coil.
How are they doing snow?
What?
Is it?
Do you really want this report on YouTube?
I got it now.
Okay. It's not solar power, so it's wind power. Winds around, okay? Okay.
Yeah, how does the solar power work?
Yeah, we'll get on to solar power when we get to solar power. Okay? You actually do it, yeah. Rightio. So, our function, no matter what it is, of a generator, no matter where we are in the world, is nearly always the same. It takes a coil, and somehow we have to use some ingenious method to make it turn. Some methods are a bit more environmentally friendly than others, and some are very unenvironmentally friendly. And Australia is one of the biggest polluters in this case because we only, well not only, but mostly burn coal, and really not exactly good coal either, brown coal, to create a lot of greenhouse gas. Okay. Rightio. Here is, thank you. Here is a diagram of a one of these. I think it actually works if I press the button. No, where are you? I'll just hold a second, I'll pause that, I'll do it. I'll put a link to this applet in the actual instructions in the actual foot of this video, but it simply goes through and shows you how we generate electricity. What we have here is the most important part is we have to have a form of spinning the coil, and here it's going to be a little handle. Okay? As the coil turns, sometimes it's fully letting all the lines of force go through, all the field lines go straight through it, and at some stage the coil goes with the field lines like now, and therefore no field lines go with it. As it turns, it cuts those field lines and generates electricity. All we need to do is, if we increase the rotation, you can see from the voltmeter over here that you get a larger swing. Why are we getting a larger swing if I spin it faster? Right, greater change of flux, greater EMF. If I slow it down, we only get, this is a little bit more than that, it'll be here forever. we only get a small, that's too slow. Okay, we get a small amount. So the greater, the faster we make that spin, the better. Now, what type of electricity comes out? Well, we've got two different commutators. There's this one, and then our old favourite, the split ring. That's a split ring one there. Okay. Now look at the type of, I'll just make it a bit faster so you can see it. Look at the type of electricity that comes out. Okay. This one I'm going to tell you is called a DC generator. It creates DC electricity. Not a constant DC, but DC in the fact that electricity only comes out in one direction. It's not constantly coming out. In other words, it goes a lot out, stops, a lot out, stops, a lot out, stops, but the lot out is always in the same direction. So when the electricity comes out, it's still moving forward. The opposite type, with a different commutator, that does say without commutator, but that's a mistake up there. With this special other type of commutator, those give you electricity that goes into two directions. Notice the needle moves forward and then back. And then it goes forward and then back. You are getting sleepy. What type of current is that? AC. That's alternating current. So with just a simple change of form of commutator, we get a different type of electricity coming out. This is DC, looking at the meter here. It goes to 0, then goes forward. It's always going in the same direction of current. Is that making sense? Okay. All we need to do is just change the type of commutator we've got. And so what are the names of the two commutators? Okay, we'll just go that one now. The two commutators for the AC, and once I say this, you're going to get them mixed up. Okay, so the AC are called the slip ring commutators. And the other one are called the split ring.
Why would they do this?
Why? Very good question. Because they don't really translate from the other languages that they're coming from.
They don't have to
Okay? Right. One is called the slip ring, and the other one is the split ring. Now, we've already mentioned the split ring. We know the split ring commutator is simply a ring which is split in half. They all have the same structure. They have a ring and two brushes. The only difference is that the AC commutator has two rings and they aren't split in half. These two rings slip underneath the brushes. The brushes are always in contact with the same ring. So I have two brushes and there are two rings, and each time the brush stays with that same ring. We know that the two brushes in the split ring, the DC commutator, it gets in contact with different parts of the coil each time the half turn happens. This one up here is always in contact with the same part of the coil. Okay, very ingenious device, but they give you two different types of current. And we're going to pause there, we're going to actually have a look at these in a dynamo at the back. So let's just pause there. So now we've had a few moments having a fiddle with the two dynamos down the back. We now know that they're really exactly the same except for the commutator. Okay? In the modern world, this is what our generators look like. They are massive, and in this case here is the actual coil, and they are inside a magnetic, they go inside these things, okay, the big pit, and it is then spun. Yep. Here is a hydroelectric one, so you can actually see, this is the coil up here. Okay, just make sure you can see the coil. So the coil is in this, right, so the coil is there, and you can see the actual there. But underneath here, more importantly, are the turbine, the fins, the propellers. And underneath here would be the water going underneath the dam, sorry, that way. And when this goes inside, it then gets exposed to the flowing river. The river would then make it turn, and that causes electricity. Okay? This is wind power. Wind power, as you know, is a very good way of creating electricity. There is no rumour, there's no foundation to the rumour that they cause sickness or anything like that. Some people think that they do cause low hums which cause sickness. We know that that is now scientifically, we've done so many studies which says that that is not true. What we do know though is that we use the air, the wind, to create that motion, and inside here all we do is have lots of cogs and gears, and here is the coil which moves in the presence of a magnetic field. Okay? And then it just generates electricity, and they all go down. It's normally a wind farm, it's not just a single wind pylon, and they all add together as with currents in series. We can, that they create, increased current. And the good thing about them is they also turn into the direction of the wind, and we've designed it to do that. Very similar to the way that we have propellers on our helicopters and aircraft. So it's a very, very straightforward and very simple thing. All we've got to do is move the coil in the presence of its own magnetic field. The last thing is, what are the two currents looking like? Where's red go? It's gone. Okay, now DC, let's go to AC generator. An AC generator creates electricity that goes up and down in a sinusoidal way. Each one of these up and down motions is one revolution of the coil. Okay? So here this is 2 revolutions of the coil. If the coil was spun faster, what would happen to this EMF? What would happen to this shape here if we spin this faster? Right, yes, it would firstly get shorter, so there'd be more, you'd go, just say I do it twice as fast, you get 2 times this. But what also, if I was to spin it faster, would I get extra EMF? Yes. So it wouldn't just double like that, it would also, it's getting there. Okay, I might just clear that off. So here we are, I'll just do a single revolution. There's a single revolution. And if I was to turn it faster, I might turn it twice as fast. I would get twice as much electricity for each loop. Okay? So this is 2 times as fast. You get 2 times the frequency, and you get 2 times the EMF. Are we okay with that? Now, if it was a DC generator, the commutator stops electricity in the bottom half coming back. So the DC generator takes this section here and reverses it as it comes out. So a negative which is in reverse becomes positive. So looking at a single revolution, you would get that, and instead of that you get going down here, you would get a absolute value graph of the sine. Okay, they're supposed to be the same hump. I'll just do that. So here we are. 1 hump, 2 humps. Okay. If I was to turn my DC generator twice as fast, I would, rather than having 2 humps, I'd have 4 humps with twice as much EMF. So you'll get, try to do that again. I'll get 1, 2, 3, 4. So this is 2 times as fast. I get 2 times the EMF, and I also get 2 times the frequency. And once again, why it doesn't go down the bottom is the commutator is reversing the current as it comes out of the coil. 2 humps is this and this is 1 revolution, yeah. But so that and that would be another revolution. So if I'm turning it 2 times as fast, the blue can give me 4 or 2. This is 1 revolution, 2 revolutions. In the space of the other one was 1 revolution.
So,
yeah.
Are those 2 humps the bottom, the negative?
Yes. So that one there is that one there.
Oh, but then what are the 2 underneath that?
So this green colour.
Yeah.
That was a single turn.
Oh, okay.
Okay. So the green colour was 1 single revolution of the coil. Okay, and the blue is when I turn it twice as fast. So I get twice as many humps and twice as much electricity coming out. Okay? The last thing I want to do is looking at EMF. Okay. Now, before we can do EMF, now I just need to know, whereabouts are you in your mathematics course? Have we differentiated sine and cos yet?
Yes.
Right, so you know how to differentiate sine and cos.
But 2 units.
2 units? Who's 2 units here? Okay, if not, you'll get very, very soon understanding what this means. Okay, now, all I need to do, we know that as we turn, thank you guys, as we turn the coil around in the presence of the magnetic field, what shape is, what's the trigonometric shape it's called? Sine, or it's cos. It can be sine or cos. Sine, you start here. Cos, you'd start high and do it that. Are you okay with the 2 difference? Okay. So, I just want you to, I'll just clear the annotations there. Right. And we'll do it I'll do it in pink. As well. Looking at the diagram here, these diagrams are on page 22. Okay. And firstly, looking at what we are doing. We are looking at flux. Okay. Here, through this coil, the coil is horizontal. Are the lines of flux fully going through? Yes, so we have maximum flux. So I'll go for a little X there. At this point here, we have 0 flux because the coil is upright in the field. The lines of flux are going on either side, like that. Okay. Here, we've got maximum flux going in the coil, but the coil's turned and it's showing its back. So it's got maximum flux, but the flux is going in the opposite direction. So it's the same amount of flux, but going back. So it's negative flux. So I'm going to put that there. This diagram here has the coil once again in the horizontal position. Is there any flux going through the coil? No. So it's 0 again. And this is back to the original position there. What trigonometric shape goes through those? Cos. So let's just draw a cos curve. Oh, that was terrible. I'll try it again. Okay? Are we okay with that? Happy? Rightio. Now, directly underneath that, so this is a cos curve. Now, underneath that, we have to draw the EMF. Now, I'm going to, my next slide has me doing the same thing, but I'm going to go and try and do it on the same thing. So, I'm now going to draw, I'll cross that one out. We're now going to EMF. The blue line is flux. Remember that? Okay. Now, we know that EMF is equal to minus N to phi beta T. Now, N in this case is simply 1. It's a single loop. So E equals minus d phi beta T. Now, phi is cos. What's the differential of cos? Cos, when you differentiate, this is d phi beta T differentiated. Goes to minus sine. But negative or minus sign?
Positive.
Positive sign. So the EMF curve would be the sine curve. Okay? Okay, we might just leave that there and we will come back to that next lesson.